What if space was not a vacuum and in fact was full of air? So the first thing I thought of, which also relates to the sun, is heat transfer. So basically there's three different ways that heat can transfer. There's radiation, which does not require a medium like air to travel through. It's basically what the sun does right now. So this is like when it shoots out, like, whatever high wavelength radiation comes out, visible light, all that, and it just goes in waves, hits the earth, and that warms up the earth. There is convection, which is like when you're boiling a pot of water and like the hot water at the bottom moves up to the top and starts cycling. So this is like the physical motion of warm air to new locations, mostly due to buoyancy and gravity, which doesn't really apply so much in space. There are mechanics that will cause some convection in zero gravity, like heat expansion and some other stuff, but I don't think any of them end up more than a rounding error with what scales we're talking about. And then the third one, which is the important one, is conduction, which is the transfer of heat from objects touching. So this is basically like if you have a hot room and a cooler room next to it, the heat seeping through the walls and everything into that cooler space. And since air is a thing that you can touch, conduction does transfer through the air. So the question is, how much heat actually conducts onto Earth? The important things are the temperature differential between the sun and the Earth. The surface of the sun is 6,000 Kelvin compared to the Earth's 300 Kelvin at around 75-ish degrees. It is the distance from the sun matters. It's 150 million kilometers to the sun from Earth. The area of the Earth, like compared to where the sun is, so if you draw a line from the Earth to the center of the sun, and you make that like a cone, that's kind of like your effective area of radiation coming out.
So like the projected area, kind of.
Yeah, the projected area. So basically, like, you have your Earth, the radius of the Earth is 6,200 kilometers. And when you do the trig to the center of the sun, from the center of the sun to the surface of the sun, you only get a radius of 60 kilometers. So basically, the 60 kilometers of the sun's surface will heat the Earth, and the rest of the sun will heat the space around the Earth. It doesn't affect it. And then the last bit is thermal conductivity, which is a property of how well air or an object will transfer the heat. And I thought this was kind of the easy one, where you just kind of look it up and see what it is. But it ended up being a little tricky, because at sun-like temperatures of 6,000 degrees Kelvin, some seemingly safe assumptions like the air is still air start to fall apart.
Much like the air does.
Yeah, so at around 4,000 degrees Kelvin, the air starts to dissociate, which basically means the O2 oxygen molecules in the air will break into just oxygen molecules. The energy will actually break those molecular bonds. And now those oxygen components are chemically reactive, and now they start messing with all the other stuff in the air, and starts actually changing the whole composition of the air. What it does actually increase the thermal conductivity, like from a linear into like an exponential when it gets to those higher temperatures. So the air stops being air close to the sun, which is pretty cool in my book. So from here you can use some pretty basic heat transfer equations to find out how much energy reaches the Earth from the sun. So total, 286,000 watts of energy reach the Earth, and based on the surface of the Earth, it brings about 24 watts per meter squared, which doesn't sound like a lot, and really it's actually not. To put in perspective, the Earth currently gets 340 watts per meter squared from the radiative energy of the sun, so we get like an extra 8% maybe, which is warm things a little bit. But speaking of that 340 watts we get from radiative energy, we have a small problem. So radiative heating, like I said, it doesn't need a medium to transfer to the Earth. It can just go through space, no problem. The issue is if there is a medium like air, it can still be absorbed by it. So basically, looking at how good the Earth's atmosphere was at reflecting and absorbing light, it's fairly safe to assume that basically none of the radiative energy from the sun will actually make it to the Earth.
That does not seem ideal.
There's going to be some crazy light shows, like, because it's all going to be refracting and, like, through prisms and all that. So there might just be, like, a crazy multicolor, like, prism of light that'll be all around the sun, which would be super cool. not super helpful for keeping our Earth warm. So actually our Earth starts to get cold instead of hot.
Well, that's counterintuitive.
But we're not done. Because we're going to have a whole new exciting problem, which is air friction. So compared to the sun, the Earth travels at about 30,000 kilometers per second, which is blazing fast. Slightly good news, speed is relative. So my assumption here is that if we're going to have the space full of air in the solar system, and for that to be even remotely stable, it means that the air has to be maintaining orbit around the sun. So when you have the source for gravitational pull, and it's huge compared to everything else, like say the sun to everything else, the speed of each thing orbiting is actually not dependent on the mass of it. Ergo, the air is moving at approximately, the air as far away from the sun as the Earth is, will be moving at approximately the same speed of the Earth.
I guess that makes sense.
And if that's happening, you won't actually have any air friction because it'll be moving the same speed. But wait, space is three-dimensional, not two-dimensional. And if the air is, say, going perpendicular to the Earth at that speed, we're going to have all sorts of problems. So who's to say the air is going to go in the same direction of Earth? And actually, theoretically, it would. So it's funny, the spin of the sun can have an effect on which way things orbit around it. It's a fairly small effect, but for when you're doing things like the formation of a solar system, it's actually at a point where you can either have prograde, which is in the same direction as the sun, or retrograde, where you're rotating the opposite direction. All the planets in our solar system, because of the small effect of the rotation, actually orbit the sun in the prograde rotation. And not only that, they actually also orbit on almost the same plane as the equator of the sun. So the Earth spins, and we're all going around the horizontal bit.
So chances are air is going to follow the same convention.
So yeah, it's a reasonable assumption to say the air is moving in that same pattern. Doesn't have a strong reason to do it, but it doesn't have a reason to do anything else.
It's
so
conforming.
in physics, it's usually good enough.
Seeing everyone else do it, it wants to fit in.
Yeah. So, fun fact. I was trying to see if this affected my calculations. It actually didn't, but I found it fun enough to share. I said we're not actually perfectly horizontal with the sun's equator. We're off by about 6 degrees. And the reason for this is not just happenstance. They say it's most likely due to the mysterious planet 9, not Pluto. So there's a planet we have not yet, an exoplanet we have not yet observed, that they scientists believe have 10 times the size of Earth and orbits at about 500 times that distance. And they had done this whole study and calculations of what influence this planet would have on the orbit of the planets in the solar system. And they calculated that it would knock us 6 degrees off plane of the sun, because that planet is actually like 30 degrees off. It's like very eccentric compared to the sun. So because it's so wonky, it actually slowly pushed all the other planets out of alignment. So that's some cool physics right there. So, like I said, the air is moving at about the same speed of Earth. There won't be any air friction. Almost.
I knew there was going to be something else.
The Earth's orbit, unlike the air would be, is slightly elliptical. The elliptical ratio is like 0.017 or something. So there's a small percentage difference of how far away the Earth is from the sun. And while the Earth does speed up and slow down to match the distance from the sun, like, you know, as it gets closer, it speeds up, and as it gets further, it slows down, like, you know, the stable orbit would, it's not exactly the same ratio as the wind would. So there's actually going to be a small difference to the tune of about 50 kilometers per second between the wind and the planet. And so it doesn't sound huge compared to the, 30,000, but 50 kilometers per second is still pretty damn fast.
Actually, wait, can I correct you on something really quickly? It is definitely 30,000 meters per second, not kilometers per second.
Oh, yeah, I think I just typoed in my notes. I'm sorry.
Put that out there. There we go.
Yeah, let me just double check my math. Yeah, my math is correct.
Okay, cool. That's a relief.
Avoided some emails there.
Yep.
Yeah, definitely avoided.
I heard it the first time you said, and I was like, I'm pretty sure I saw 30 kilometers per second, but I should double check that before I correct you.
I didn't even register it because I was just like, that's a big number. It sounds right.
Right, exactly. Space is big, guys. Anyway, continue.
Yeah, and also I'm gonna correct myself one more time. I wrote 50. What I mean is 250.
How did you mess that up?
It's 204. It's 200. It's 250 meters per second. Is the speed difference?
There we
I'm
go.
getting there. There's a lot of fucking math. My spreadsheet is humongous. So I took this speed difference, coefficient of drag, density of air, area of the Earth, calculated my drag force out. Is going to be 2.11 times 10 to the 18th newtons of drag force on the Earth, which is a really big number that doesn't make a whole lot of sense. But what this means for the Earth is basically the Earth is going to be going through this, and all that energy is going to be transferred to heat, and the Earth is going to heat up.
Oh, so you're bringing it back to heat.
I'm bringing it back to heat again because, you know, we were cold before. We're going to warm up now. And doing the math out, the time it would take to heat the air by 1 degree is about 550 seconds. But we get a little extra because the Earth is also emitting heat at the same time. The Earth actually emits about 10% of that away as heat in the same time frame. So we're not actually too many orders of magnitude off a stable heat equilibrium. But basically every 10 minutes, the temperature of the Earth will increase by 1 degree.
Okay.
So how do we fare as a people going through this here? The human body can withstand for 10 minutes approximately 140 degree heat. So it takes about 11 hours from our baseline to get to that temperature outside. So you have about 11 hours to live, which
not
is
bad.
longer than we usually give people.
Yeah.
Yeah, usually it's pretty instant.
And better news, if you are in an air-conditioned building, air conditioning can, you know, cool the air by about 20 degrees in its cycle. So you can get like an extra 4 hours there. And
There
even
you
more
go.
if you're pretty well insulated. And but like the last thing, like if you really knew this was coming and planned for it, if you went underground or even better yet, like a submarine, you might be able to last for like quite a while. The Earth gets pretty hot. I guess almost luckily, the amount of heat it emits is the temperature is to the 4th power related to how much heat you emit. So it emits a lot more heat per degree temperature. And we actually start balancing out when the Earth is about 476 degrees Fahrenheit.
Well, that's
So
not
when
bad.
we have a surface temperature of that, a little balmy, we will have reached equilibrium with our speed, our air friction force. So that's about as hot as the Earth will get.
Well, that's a relief.
Yeah, just only 476 degrees, which
Good
is
to
totally
know.
survivable.
Yeah.
One last thing I looked at, just real quick, was, you know, you're having air friction. It's slowing down the Earth. Are we just going to lose all our momentum and crash into the sun? And based on the kinetic energy the Earth would have going around and how much it loses, so the kinetic energy is on the order of 10 to the 33 newtons is how much energy the Earth has. We lose 10 to the 18th per second, which is like 15 orders of magnitude lower. And so basically, before we lose half our speed and really start running into orbital problems, I've calculated that it'll take about 9 million years before that's a problem. So that one's not going to kill us.
It only takes us 11 hours to die.
Hey, 14, I got AC. Yeah, so that's all the space facts I learned this week.
A lot of death in that one.
Look, there's barely any death in that one.
Only the whole world.
Look, I gave them like a whole 12 hours to get their affairs in order.
That is longer than we usually give the planet in these
Yeah,
situations.
that's true.
Like, you can finish out the workday and like go out for a few drinks and then you die.
You would finish out your workday?
Well, I mean, I'm not sure if you would know it was coming. Like, it would just start getting warmer and then like, be like, wow, it's 120 degrees out. What the fuck? And then you would be like, wait, maybe I should start panicking.
And then you have a drink is your next plan after the workday because you're hot.
Although I guess there would be clues. For example, the sky would no longer be blue. The sky would probably be fireball.
Yes, yeah.
Colored. Because part of my assumptions here was that we'd only have about half our atmosphere, assuming that the top half of the atmosphere would kind of just be a chaotic mess of nothing and not really count to helping us. So yeah, that is what would happen if the Earth, the universe, the space was full of air.